Hello everyone. So my name is Ryan, and today we are going to be talking about blind bistatic radar parameter estimation in Doubly dispersive channels. I would like to take a moment to thank my co-authors, Ando uh, and Eric, and Professor Abru, of course. And also this work was done in a collaboration with Andreas from the Fraunhofer Institute. So let's jump right in. Um, so here's a rough outline of what's to come. We have a small introduction, and then we go through the system model, and then we go through the blind estimation framework, and then we show some results. So as an overview, we study the blind bistatic RP problem in ISAC systems. ISAC is a well-known scenario where we try to estimate radar parameters using communication waveforms, at least from the perspective of communication-centric ISAC. And what we mean by bistatic is, so this setup assumes two base stations, one active, one passive, and the active base station transmits signals. And we assume that some passive base station, it doesn't have to be a base station, it could also be a UE, for example. It obtains some signals, and we want to estimate some parameters of the surrounding scatterers, so the ranges and velocities using these signals that we receive. And for the choice of waveforms, since we are working in doubly dispersive channels, and since AFDM has so far been the competition to beat in these types of channels, we will give our derivations for FDM, but in a very general manner, so that the consequent OFDM or OTFS waveforms can also be applied seamlessly. So when we talk about blind scenarios, what we mean by blind here, to clarify, is that the receiving base station or UE has no knowledge of the transmit signal. So this is actually one of the distinguishing features from past work that has been done here, because even in usual bistatic ISAC setups, or even, for example, passive radar from the radar community, there is always an underlying assumption that the pilots, or rather some reference signal, is known at the receiving base station or receiver, right? So we now want to completely remove this assumption and do it completely blind, such that there is no knowledge of the transmit signal at the receiving base station. So how do we do this? How do we estimate radar parameters without knowledge of the transmit signal? So let's now jump into our system model. So as I described before, we have an active base station transmitting signals, and a bistatic base station also receiving the transmitter signals. And of course, we have a bunch of targets in the surrounding present in the system. So one nice thing here is that since we are working with OFDM, OTFS, and AFDM waveforms, what we're transmitting is actually communication waveforms, right? So there's absolutely no reason that we can't transmit at the full rate without losing any spectral efficiency with this waveform. So these targets can also be UEs, which want to get some data, and this bistatic base station would want to estimate the ranges and velocities of these targets in the surrounding. So that's our goal of the bistatic this bistatic ISAC setup. So jumping straight in, we consider straightforwardly the typical doubly dispersive environment, which is modeled by equation 1 here. So this looks very familiar for those familiar with doubly dispersive channels, because you have your usual complex channel gain, you have your Doppler shift, and you have your delays. So this channel is defined for all P targets. So each P target has an associated Doppler shift, aka velocity, denoted by nu p, and tau p, which is the delay correspondingly, which gives information on the range of the target from the base station, right? So now this is the typical general model that we have, and then correspondingly, the time domain input-output relationship is given by equation 2 here. So equation 2 also explains how all of these effects can be concatenated into this matrix that's given by this psi. So psi incorporates the complex channel gain, phi p, which describes the effect of the cyclic prefix depending on the waveform that's used. And this omega p is going to be a diagonal matrix which describes how the Doppler shifts affect the subcarriers in the channel. And finally, this pi matrix is a cyclic shift matrix which describes how the delays are going to affect our received signal. So these are correspondingly defined in equation 3 and 4 here. And now we dive into the AFDM transmit signal. So we have the typical structure from equation 5 where we multiply symbols from an arbitrary constellation, take for example POM, and modulate it with this effective matrix where, as you can see, this AFDM is just the typical OFDM normalized DFT matrix sandwiched between these two lambda matrices. So we are effectively tuning this DFT matrix and shifting the diagonals to increase the robustness towards the high Doppler shifts in doubly dispersive channels. So there's more literature on this, and you can look up the references for AFDM here, where, as you can see here, this lambda is defined as in equation 6. And this lambda 2 can be chosen as a free parameter, so the corresponding C2. But C1, in this case, is going to be governed by the maximum Doppler shift in the channel. So straightforwardly, the received signal can be given by equation 7, where we had that psi from before. And this is the time domain relationship, right? And now we can demodulate this signal as follows to get equation 8. And putting it all together, we have the final input-output relationship given by equation 9 and 10. So as you can see, in the discrete affine Fourier domain, which is the foundational domain in this AFDM waveform relationship, where this AFDM comes from, you have this nice GAFDM matrix, which incorporates all of your channel characteristics. So you have this complex channel coefficient and this matrix with the cyclic prefixes, the Doppler shifts, and the delays, right? So if you estimate these FPs and these LPs, you essentially have the delays and the Doppler shifts of the target in the surrounding. So, and as you can see, the modulation will only kind of shift the diagonal matrix, the band diagonal matrix, which is going to be cost as a consequence. So moving on to the blind estimation framework that we have proposed. Let's first rewrite equation 9, the input-output relationship, as in equation 11, since we want to keep this general, and we can write this for any waveform. So we now get equation 12 here, where H is now this wide matrix, and gamma is this tall matrix, right? So this is just simple reformulation, and it's equivalent. So now we can consider a stream of T transmitted frames and extract this matrix relationship where these are just the frames that we have. So each X in here contains T frames, right? So this is now an N by T matrix, and the corresponding things hold for the others as well. And we can now also compute a sample covariance matrix from this formulation in equation 15. And that's given in equation 17. So provided that we have like a normal symbol constellation, a normalized symbol constellation, for example, we can always normalize the symbol constellation that we use, and we use a sufficiently large number of T. Equation 17 can be approximated as given in equation 18, where the sigma squared W is the variance of an arbitrary column in W tilde that we used before. So setting the symbol constellation power to 1, equation 17 can also be written as in equation 19, right? So as you can see here, when the number of frames goes to infinity, we achieve a perfect covariance matrix in that sense. So we can now use the definition that we had before for this H and the gamma and define this covariance matrix in terms of these two sums, as seen in equation 20. And we can now define a big H of G, which is just the H vector times its Hermitian. And we can represent each PQ element in HG as given here. Yeah. And now, using the definition, we can rewrite equation 20 as in equation 21. As you can see now, this gamma tilde of PQ is concatenates both effects of this P and Q, right? So now, since the previous formulation was still based on n by n matrices, we simply do a summation on the rows to get equation 22, as since all the characteristics of these gammas are present in the off-diagonal elements. So doing a sum does no harm here, and we can just get this equation 22 as it is, where this new E of PQ is defined as in equation 23. So there's each column of this is given by this this type of formulation, and I think the corresponding E's are defined in equation 27. So before we get there, we have to first do a slight change to our original doubly dispersive channel. So instead of writing it in terms of arbitrary paths, we simply rewrite it in terms of a maximum delay and Doppler shift, right? So we can do this since most baseband systems, at least typical wideband systems that have been using communication systems, can be defined using a maximum delay and Doppler. So we can just rewrite the previous equation 1 as equation 24, which lets us reformulate our matrix relationship that we got in equation 23 as in equation 25, where we now have this explicitly defined dictionary matrix, right? And this is in fact, this is actually what allows us to completely remove the dependence of the transmit covariance from this framework. So now what we want to do is we want to minimize this equation 28 such that we can extract this Hg bar. Since Hg bar now contains all of the information that we need on the delays and Dopplers, and this is actually a sparse vector. So once we estimate this sparse vector, we can now extract the indices of the sparse vector, which gives us the knowledge of the delays and Doppler shifts of the p path. So now, as you can see, the typical easiest formulation to do this minimization is via lasso kind of framework, where we have the typical L1 norm present here. However, we want to do one better, and we can reformulate this as stronger as given in equation 29. So as you can see, we now have one second. So we now have a problem. We still have the lasso, but we now enforce that the rank of this Hg is 1, and that we also incorporate a zero norm approximation such that we now enforce the sparsity of the system. So as you can see, this problem is now completely non-convex, and we need to find a way to solve it, convexify it, and solve it. So what we can do is we can now write this equivalently as equation 30. As you can see, this eta is now a weight parameter of the L0 norm, and we have this L0 norm here present to enforce the sparsity. And here we can now use a technique called fractional programming to replace this L0 norm, which is a tight approximation, and then we can minimize this accordingly. So the L0 norm approximation can be seen here. So equation 31 denotes how we can reformulate this, and this can now be convexified via this fractional programming framework to give as seen in equation 32. And of course, this alpha is a tightness hyperparameter, usually chosen to be a small number typically. And so our final relaxed problem becomes equation 33. So this is now this is now convex and can be solved via typical solvers like CVX, for example. So this is the final algorithm that we have. It's just a summary of the whole framework that we discussed, and this will give us now a sparse solution which we can use to estimate our taus and nus, giving us our ranges and velocities. So to see how this performs, let's first take a look here. So in terms of range RMSE, as you can see, we now use the AFDM waveform with 64 subcarriers and estimate 2 paths. And as you can see, the performance increases significantly when the number of frames that we use increase. As you can see here, when t is infinity, we actually reach the threshold really fast, which is like the theoretical bound that we can reach with this blind type of framework. And it's a similar story for the velocity RMSE. As you can see, when the number of frames increase, the RMSE also decreases accordingly. So this was it. Do you have any questions?
Thank you, Ryan. I have a very good job, by the way. Thank you very much for the talk. I have one short question. In your results, if you could go back to the results.
Yeah.
Yeah, so I mean, of course, this is very nice, and to the best of my knowledge, it's the only method so far that is completely blind as it is. But obviously, when you look at the results here, the Achilles heel, so to say, is the fact that you need quite a large number of samples, right? Of time to
Yes.
convert to a solution. And I believe that this is probably not, avoidable. But my question is, what if the channel changes somehow? Is it possible? Do you think it's possible to do anything to somehow um, enable us to be observing the channel and the target over a larger period of time and still obtain some information? Or what would happen if the channel keeps changing within this, let's say 10,000? We see here that with around 10,000, you get a pretty decent RMSE. Yeah, so my question have you investigated the robustness with respect to the channel variation over time and so on and so
Um,
forth? So what could you tell us about that?
okay. So good question. Well, not really, because this was a preliminary work to see if we can somehow formulate a completely blind problem to do this parameter estimation. But yes, as you say, I think if the channel changes within these 10,000 frames, we can probably get somehow try to track the channel as well. But this will have also this will need to be incorporated into the problem as well, because if the channel is constantly changing throughout from each, let's say that it changes at every frame instance, that would pose a problem.
Yeah,
But if it
yeah,
if it
that's way too
changes,
fast.
like,
Mhm.
yeah, if it changes every couple of hundred, for example, then it's not so bad, because then we can track it somehow and use that knowledge in the estimator framework. So yeah, this is potentially some future work to be done.
Okay. All right, thank you. Anybody else? Any questions, guys? Comments?
Um, Ryan,
Yes.
thank you very much for the presentation. Um,
Yeah.
I'm one of the things that comes up again, very similar to the number of samples that is needed. How does this
Mhm.
affect the complexity of the of finding the solution? Is it really feasible to perform this type of calculations, so to say, in real time for a large number of samples?
Well, also a good question. I mean, the algorithm as a whole does have a high complexity, since as of right now we are solving it using these interior point methods. But there are, I think, some variations that can be used. For example, there are some frameworks that we can somehow apply to reduce the complexity. But yeah, you are right that for example, with 10,000 frames, the algorithm itself could probably not operate in real time.
Thank you very much.
Yeah.
Thank you. Thank you, guys. Then again, and yeah, see you next time.